Welcome to this demonstration of using the Autodesk Nastran In-CAD solver embedded in Inventor. This technology enables designers the ability to solve problems that go beyond the capabilities of linear static and frequency studies that are currently available in Inventor Professional. Using this hedge trimmer assembly, we'll focus our attention on the nonlinear options available for the material library as well as the solver. The guard on the hedge trimmer is made of thin plastic. Typical load conditions on the part cause a large amount of displacement. Linear static studies may provide designers with the highest stress location or displacement in the design. However, in order to gain high-fidelity results, the nonlinear static study is required in cases such as this. Here you can see we have the entire hedge trimmer assembly open in Inventor. We'll turn off the other parts and focus on the guard. Our goal is to ensure the component will not fail under extreme load conditions and ensure the safety of the design. There is a Nastran tab in the ribbon, as well as a feature tree for making the setup easy and remain in the CAD design environment. Let's begin by starting a new analysis. There are several options available for different types. There are static and dynamic loading conditions for linear and nonlinear material, linear and nonlinear buckling, frequency and random vibration problems, fatigue studies using constant amplitude loads, as well as vibration fatigue. Steady state and transient heat transfer are also available. The material library for the study can be selected from a standard library or imported directly from the CAD model. In this case, we only want to analyze one of the parts in the assembly, so we'll select the guard and confirm the material we want to use. Autodesk Nastran provides a wide variety of material models to choose from, starting with orthotropic and anisotropic for non-uniform material strength. Hyperelastic options include Neo-Hookean, Mooney-Rivlin, Ogden, and more for rubber-like parts and biological tissue. Brittle, concrete, foam, multi-continuum technology for composites and fibrous material, Nitinol for parts made from nickel-titanium alloy such as braces, spectacle frames, or artery stents. And finally, viscoelastic for parts that have both viscous as well as elastic behavior, such as an insole found in footwear. Here we'll use an isotropic material using a nonlinear stress-strain curve. You can see here we have settings for nonlinear elastic and elastoplastic for analyzing the behavior prior to yield. Let's say we know the material yields at 40 megapascals. We'll use a simple two-point curve to define the behavior of the material. Inside this dialog, there is an option to check the curve for a quick visual overview. Notice that the material softens greatly after it reaches its yield point. There is also an option for isotropic and kinematic hardening for fully applying the load in opposite directions or fully reversing the load. Or imagine bending a paperclip past yield in both directions. Next, we'll apply some boundary conditions. We're going to set up a virtual test that resembles the use of the design in real-world conditions. The guard is going to be constrained at the base so it doesn't move from the body of the trimmer. And we'll also apply a load to the front face of the guard for simulating a collision with an object. We'll use a value of 333 newtons, or about 75 pounds. Slide bars make it easy to see each of the boundary conditions on the graphics view. Before running the study, we'll mesh the part or divide the geometry into several pieces to be analyzed. There are many types of elements available, such as tetrahedrons, shell elements for thin components such as sheet metal, and beam elements for models such as weld frames or spokes in a bicycle wheel. The real power behind running a nonlinear analysis is the solver. Taking a look at the setup, you'll notice an option to define the number of iterations. The solver will apply the 333 Newton load in increments and update the stiffness of the model along the way. This is more accurate than linear static studies, which apply the load in one increment without updating the model stiffness. You will also notice the results are displayed while it's being solved. They are also shown in the graphics view, as well as saved to a file so users can stop the calculation at any point and view the progress of the load. We can already see that the highest stress in the model is getting close to yield even before the solution is complete. This is a huge time saver, enabling designers to take notes early during calculation. There are many options available for results. The display plot will help us to determine how far the guard is deflecting. We can view the results at any point during the load. This may come in handy when applying a variable force that is loaded and unloaded. Here's a view of the displacement plot at 10 times the actual deformation. There is also the ability to animate the behavior of the model. And these animations can then be saved as a video that can be sent to customers and coworkers to review. Let's take a look at a couple other result types. The von Mises plot shows us where we have areas of high stress. Notice that the highest stress is 43 megapascals, which is beyond yield. There is a good chance the guard will not bounce back to its original position after the load is removed. By changing the minimum value on the legend, this is one way we can quickly see where the material is yielding under this load condition. Let's make a change to the model to see if we can improve the design. We'll make the length of the rib longer by changing the angle from 40 degrees to 50. Any modification to the geometry can be remeshed and analyzed immediately in Inventor. In other words, there is no need to pass the model to another application for the updated results. And once again, the results are displayed while it's being solved. This way, the designer can determine whether the change to the model is having a positive impact even before the solver is finished. Decisions can be made faster without the need to wait or walk away from the computer. Let's take another look at the von Mises stress plot to view the final results. As you would expect, we're observing the results that would pass for a safer guard to be used with the hedge trimmer. The highest stress is 25% less with the longer ribs. We could of course take it a step further by thickening the ribs as well as the thickness of the overall model. Or we could also experiment with other material types. Each time a new study is run, there are countless hours that are saved as opposed to manufacturing a physical prototype. Using Autodesk Nastran In-Inventor helped us to ensure the safety of the hedge trimmer assembly. We can now confidently move on to innovation in other areas of the design.